When an advanced space observatory turned its highly sensitive instruments toward Pluto, the findings exceeded all prior expectations. The resulting visuals weren't just the clearest ever obtained, they completely altered how we perceive this distant world. For a long time, Pluto remained a remote enigma, shrouded in frozen obscurity. Even after the landmark 2015 flyby by NASA's New Horizons, many of Pluto's characteristics remained uncertain. With the help of powerful infrared imaging and exceptional resolution, scientists are now able to observe Pluto with an unprecedented level of detail. This new insight has profound implications. Once classified as the 9th planet in our solar system, Pluto continues to captivate researchers and astronomy enthusiasts alike. Located in the Kuiper Belt, more than 3.6 billion miles from Earth, Pluto has always posed significant challenges. To study, previous telescopes, including those long considered top-tier, could only provide faint and blurry glimpses of its surface. However, a new era of observation has emerged. Instruments stationed far beyond Earth's atmosphere, equipped with a vast mirror and advanced tracking capabilities, have changed how distant celestial bodies are studied. These tools can detect subtle differences in light from far-off targets, revealing surface details, weather patterns, and geological features never observed before on Pluto. What makes this achievement even more notable is the method of detection. Instead of relying on visible light, these instruments operate primarily within the infrared spectrum. This allows them to pick up heat signals and slight temperature fluctuations invisible to traditional optical equipment. Applying this technology to Pluto has enabled scientists to peer through its faint atmosphere and study surface ice dynamics and signs that may indicate ongoing geological activity. One particularly detailed image recently shared by international space agencies showcases Pluto's complex surface with astonishing clarity. These observations captured diverse features, including expansive nitrogen ice plains, rugged highlands, and possible seasonal variations in the atmosphere. Among the standout features is Sputnik Planitia, the heart-shaped region initially observed during the New Horizons mission. Although already identified as being composed mostly of nitrogen ice, the new infrared data reveals depth, texture, and brightness changes, suggesting surface processes may be actively shaping this area, potentially involving sublimation or the redepositing of ice. Despite Pluto's extreme cold and distance, recent observations have also provided new understanding of its sparse atmosphere, which consists primarily of nitrogen with smaller amounts of methane and carbon monoxide. While incredibly thin and frigid, Pluto's atmosphere shows subtle changes in composition and temperature that are now being tracked over time. This allows researchers to better understand the planet's long and complex seasonal shifts, which unfold over its 248-year orbit around the Sun. Beyond Pluto itself, enhanced imaging has also yielded clearer views of its 5 moons, particularly Charon, the largest and closest of the group. Nearly half the size of Pluto and tidally locked in its orbit, Charon has long intrigued scientists. Recent data shows more about its surface composition, possibly including frozen ammonia, organic compounds, and indicators of a once active geological history. The smaller moon Styx, Nix, Kerberos, and Hydra have also come into sharper focus. Previously difficult to study due to their size and distance, researchers can now more accurately chart their orbits, analyze their surface materials, and investigate their origins. These discoveries contribute to a more complete picture of Pluto's system and offer valuable information about the processes shaping the farthest regions of the solar system. Perhaps one of the most intriguing aspects of this new data is how it could influence the ongoing discussion about Pluto's classification. Though it was redefined as a dwarf planet in 2006, the new findings suggest a complexity-layered terrain, a dynamic atmosphere, and potential subsurface oceans that rivals that of recognized planets. This challenges past definitions and renews interest in what truly constitutes a planet. The newly detailed images also emphasize the scientific importance of exploring the broader Kuiper belt, home to thousands of icy bodies orbiting beyond Neptune. With improved clarity, researchers can now focus on similar distant objects, like Clearest and Makemake, with greater precision. Every new observation adds to our understanding of how the solar system has formed and evolved over billions of years. In contrast to instruments that observe visible and ultraviolet light, this new observatory excels in the infrared range, allowing it to see through cosmic dust, detect faint heat emissions, and observe objects too distant or cold for previous methods. This is particularly important when examining icy celestial bodies like Pluto, which emit minimal visible light, but become more distinguishable in the infrared spectrum. Capturing such fine details of Pluto had extraordinary tracking precision. The telescope had to follow a small, swiftly moving object, all while compensating for its own movement and Pluto's slow drift through the star field. This feat demonstrates the instrument's adaptability, capable of studying both the oldest galaxies and active, nearby worlds within our own system. This flexibility paves the way for future exploration of other far-off targets, such as Neptune's puzzling moon Triton or additional large Kuiper belt objects. With every new observation, more of the outer solar system is unveiled, regions still largely unexplored and rich with scientific potential. As experts analyze this new wave of data from Pluto, more questions emerge. Could a subsurface ocean exist beneath its frozen shell, like those believed to be on Europa or Enceladus? What forces might drive geological activity in such a remote and frigid environment? Could cryovolcanoes be reshaping the surface and releasing hidden materials from beneath? Although this single mission can't answer all these mysteries, it offers crucial leads to guide future research and potential missions. One exciting outcome is the opportunity to compare Pluto with other icy worlds. By studying similarities and contrasts between Pluto's nitrogen cycles and Triton's, examining its organic chemistry against Titan's, or investigating whether its crust bears signs of ancient impacts or chaotic formation, scientists can deepen their grasp of planetary evolution, both within and beyond our solar neighborhood. Yet perhaps the most powerful effect of these findings is symbolic. Not long ago, Pluto appeared only as a blurry dot in even the most powerful telescopes. It was an obscure, unreachable destination. Today, we can view its rugged peaks, icy fields, and fragile atmosphere in extraordinary clarity. We can trace patterns in its iconic heart-shaped plane and witness the delicate motion of its satellites. These advancements represent far more than technical progress. They attribute to human curiosity and determination. Every image and data stream reflects the work of countless scientists, engineers, and thinkers who strive to push beyond known boundaries. This new vision of Pluto reminds us that the universe still holds endless secrets for those with the tools and tenacity to uncover them. From its discovery in 1930 to the close encounter in 2015, and now to this phase of deep observation, Pluto's story is one of evolving understanding. These observations not only sharpen our view of this distant world, they mark the dawn of a new chapter in the exploration of the outer solar system. This is more than just a new image. It is a significant milestone. It offers a vivid glimpse into a world once beyond reach and suggests that so long as we continue to explore, the cosmos will continue to reveal its mysteries.